Good morning. Today I'm still going to talk about rate of escape, but I'll focus on a lower bound. And the setting I want to work is a Cayley graph. So we start with G, which is a finitely generated group. So there is some set of generators S, elements of the group. We'll take the set to be symmetric. So with any element, we also take the inverse. And so the Cayley graph is just has vertex set, which is just the same as the group, and then we just have to define what are the edges. So x and y are neighbors if and only if x is in ys, and it's the same as y is in xs because of s is symmetric. So this is a Cayley graph, and of course the most standard examples would be ZD with the standard basis being generators, the standard basis and their negatives, or a free group, which gives you right. So for instance, F2 with two generators. So we have A and B, and then this is A inverse, this is B inverse, and you keep going, and you get a 4-regular tree for F2. Or you could build any tree as a free product. And there are many, many other Cayley graphs. There are interesting Cayley graphs of polynomial growth beyond ZD, like the Heisenberg group. And so now we're going to do simple random walk, or lazy simple random walk, it won't matter. So simple random walk on such a Cayley graph. I want to see how fast it escapes from the starting point. And the basic type of theorem I want to show is this: the expected distance. So I'm going to use rho today for the distance between x0 and xt, is going to be bigger than some constant, will be more precise, times t. And OK, and so we want to prove a statement about the distance squared is going to grow linearly. So distance squared, of course, if you do random walk in ZD, then just by calculating the variance, we know that the expected distance squared indeed grows linearly. If you walk on a free group or a free product, so on a tree, then actually the expected distance from the starting point grows linearly. So the expected distance squared will even grow quadratically. But we want to show that at least linear growth is going to be true. And we want to prove that for finite and infinite groups. So of course, for finite, there's a problem. This can't hold forever. So for finite, it will be until some time. So we want to prove this for all t. If G is infinite, and all t until some number that we hope to make large if G is finite. So even in finite groups, we think of a huge finite group. We want to say that until some time, and part of the game will be to make this time as large as possible, the distance squared grows linearly. And as in many examples, there's the infinite group can give some hints for the finite case, and vice versa. So in a way, in some ways, the infinite group case is simpler because there's no termination time. This kind of bound will hold for all time. In the finite case, we have to stop it at some point, and that game will come in. So let's first think of infinite groups, although our emphasis will be on finite. And by the way, I will relate these to mixing bounds later, but for now we're just talking about rate of escape. So for infinite, it seems very natural that this should hold, because if you think of a Cayley graph, the Cayley graphs we know, you always move at least as fast as on Z. So on Z, we know the distance grows like square root t, the distance squared grows like t. So it seems like if you have any Cayley graph, you should move away at least that fast. There cannot be bottlenecks that will stop you. Well, the conclusion is right, but the intuition is wrong. So I want to say that there's no coupling proof, and also there cannot be. I'll explain what that means. And there's no heat kernel proof, but there could be. And the only proofs that exist are based on spectral embedding, and I'll make this. I'll make this precise. So what would be, for me as a probabilist, the most natural idea, if I look at the Cayley graphs we know, the simplest ones, then we think, well, every vertex, it should be true that at least half the neighbors should be further from the origin than closer. That's true in ZD, right? Any vertex, at least half its neighbors are further from the origin than it is, or weakly. And so it suggests that maybe we can couple random walk on the group with some delayed simple random walk on Z. And we could do that for ZD. And we certainly can do that for a tree where we move even faster. And then somehow give a coupling argument. Now this fails badly because there are Cayley graphs with dead ends. So there are Cayley graphs with dead ends. So what's a dead end? So dead end is a vertex where, so here is the origin, say the identity, and here is a dead end, means all neighbors are closer to the identity than the vertex itself. So you walk trying to escape from the identity, and you get stuck at a point where every step actually gets you closer. And at first, how can the Cayley graph behave like that? So let me first give you an example. So I'll describe to you what is the graph. So the example is one of all-time favorites. The lamplighter groups will do the lamplighter group over Z, which we sometimes write like this. And this group can be defined in terms of the group operation. It's a Rieth product of the integers mod 2 with the Z. So if you're an algebraist, then the word Rieth product should do. But I want to describe what is this graph. How does the Cayley graph G look like pictorially? So I'm going to draw for you not the Cayley graph, but an element of the Cayley graph. So an element of the group really is obtained as follows. So it's a sequence of zeros and ones, which we think of as on-off lamps. But only finitely many lamps are on. So we have a sequence of zeros and ones with finite support. So it's eventually all zeros. But there are some ones that represent on lamps. And in addition, we have a marker pointing to some integer. Okay, so formally an element of the group is a pair, px, where psi is in 0, 1 to the z, but finitely supported. So that's the lamp configuration, and x is some element of z. This is an element of the group. And one can define the multiplication operation. But instead, all I care about is to tell you who are the neighbors of an element of the group. Also, the Cayley graph structure. So that gives you both the group and the generators. So the neighbors are very simple to describe. They are obtained by either taking x, the marker, and moving it right or left. These are the neighbors. And the other neighbor is taking the lamp and flipping it. Okay, so we have 3 neighbors to any state. But in fact, this construction can be done over any base graph or any base group. So here I took the base to be z, but you could do this more generally. And in particular, you can get interesting finite groups by taking the base to be, say, a cycle and have labelings of a cycle. So those are actually important examples for mixing. But here I'm looking at the infinite example. Okay, is it clear what is the graph? This picture is not the picture of the graph. It's just an element. One vertex has this representation, sequence of 0, 1s, and the marker. And the neighbors of this element are obtained by either moving the marker or flipping the lamp. Okay? So look at this group. So first, to get oriented, what is the growth of this group? So remember, the ZD has polynomial growth of order D. The trees have exponential growth. What about this group? What is the growth rate? Polynomial, exponential, something intermediate? Exponential, right? So it's easy to see that if you, so for instance, in n steps, I could get to any configuration of the first n over 2 lamps. So if I start, so the identity of the group is just this all 0 configuration and marker at the origin. And now, in n steps, I could get to any state of the first n over 2 lamps, because I just walk and turn part of the lamps. So that shows me that that in a ball of radius n, I have at least 2 to the n over 2. If you do this more carefully, you see that you can get actually a Fibonacci number of sequences within n steps. And the growth of this group is really given. So if you look at this, the ball of radius n in this group G, and take the nth root of the size of that, it goes to the golden mean. That won't be important for us, just a curiosity. OK, so this is a group of exponential growth. So normally, if you think of a group of exponential growth, the ones we're familiar with, the trees, the walk goes very fast. Well, here the walk doesn't go that fast. It goes just like in Z, no faster than in Z. Because now, how does simple random walk behave on this group? After all, we start here. So the marker is just doing a simple random walk with some delays. So by time t, the marker will only go to distance root t, typically. After all, it's just the maximum of a simple random walk on the integers also has scales like root t. And so all the lamps that will be on will be within distance root t, typically. And so if I walk for t steps, then with high probability, I can get back to the origin in root t steps. So if I do a random walk of t random steps, then the distance from the origin is typically going to be just root t, because I can go and systematically turn off the lamps that are on and bring the marker back to the origin, all in time, which is some constant root t, so with high probability. So it's very easy to show that in this case, the expected distance squared at time t grows just like constant t, even though we have exponential growth. So it's very important to have examples, because when people thought of these questions abstractly without examples, they conjecture that, oh, exponential growth must mean positive speed. But it doesn't. OK, now I said about dead ends. Look at this group and look at a configuration like this. So I have 1s, say, from minus n to n. And the marker is at the origin. And then 0s outside. Well, if I want to go from this configuration to the identity, what do I have to do? I have to go all the way to the right, turn off these lamps, and then sweep back all the way to the left, turn off these lamps, and then bring the marker back to the origin. So you can calculate. The distance. It's like 6n or so. But the important point is, if I start in this configuration, any step I do helps me getting back to the identity. Because what can I do? I can either switch the lamp off where I am. Well, that's something I need to do to get back to the identity. Or I can start walking right or left, but that's all stuff I need to do. It doesn't matter in what order, in order to get back to the identity. So any step, if you measure the distance to the origin, any step brings me closer. Of course, this is a somewhat special configuration, but it's not unique. So if there were lots and lots of these configurations, then the walk would be very confined and wouldn't move at all, or wouldn't move very fast. We do know, it's easy to see, that the walk does move. I mean, the lower bound of t, it's very easy. On the expected distance squared, it's very easy because it's true for, just for the marker. But the fact that there are dead ends here means that we have no chance of doing a coupling proof by taking our walk on the group, a walk on Z, and saying at every step, the walk on the group is going to move more away than the walk on Z, because the walk on Z does get further with probability half every state, while the walk on the group sometimes could be forced to move back. So coupling, which is the first go-to for most, for me as a probabilist, really fails. Now another natural idea is to use a heat kernel bound. So by that I mean bound on the transition probabilities. So for instance, take a group like this with exponential growth. You could do it in other cases. Suppose I can bound the probability of time t of being at any individual state, and I have a really good bound. Then I can sum this bound over a ball around the origin, and if this sum is small, I'll conclude that it's high probability I'm outside, so the distance is growing. Something like that is possible, but it will not give the sharp bound. So for instance, we have this theorem, going back to, again, to Varopoulos, a different paper of Varopoulos, which says if G has exponential growth, then it implies that the simple random walk satisfies the probability, all the transition probabilities are bounded by some e to the minus constant t to the 1/3. Okay. Now, if I want to use that, then I can, if I take a ball of radius r, which is a small constant delta t to the 1/3, then by choosing my delta small, I can ensure that the probability I'm in this ball is going to be small, right? Because any individual point has chance, e to the minus this chance. The number of points in this ball is only growing like e to the constant r. So comparing these two, I see that the overall chance of being in the ball, just as a union bound, is is much less than 1. So if I choose just delta as a small enough constant, so I'm likely to be outside this ball, which means that the expected distance is going to be at least t to the 1/3, constant t to the 1/3. So expected distance squared is going to be t to the 2/3, which is something. It's not trivial, but it's not what we want. And this estimate cannot be improved in general. And indeed, again, the lamplighter group is an example. So if I take the lamplighter group and I ask, what's the chance that at time t, I'm back at the starting point? I claim this is about e to the minus constant t to the 1/3. And to see that, just take some neighborhood of radius of size L, which is t to the 1/3. And what I want is, I want to force the marker to never stray out of this neighborhood. What's the chance of doing that? Well, an interval of length L, in time L squared, it's just a constant probability to stay in that interval. So in time L squared, I would stay with constant probability. And I can also ensure that at the end of this period of L squared, I'm in the middle half of the interval, not near the edges. And that will only cost me a constant. So so on the Lamplighter group, the probability, so starting from any W which is in minus L over 2, the probability starting from W that at time L squared, the walk is again in minus L over 2, and the max over all times j less than L squared of xj. So by x, I'm just recording now the marker. So I'm interested in the Lamplighter group, but now I'm just looking at the movement of the marker, which is just a random walk on z. And I want this max to be also less than L. These probabilities are constants. That's just basic facts about random walk on z. So this is some, this is some positive. Well, what I care about, it's greater than some positive constant, which I'll write as e to the c. And now we can just iterate that, because I proved it, we observed this not just starting at the origin, but starting at any point in the interval minus L over 2, L over 2. This is true. And then you can just iterate that. How many times do you want to iterate? T over L squared times. So we get the probability that the maximum over all j less than L squared of xj, I'm sorry, over all j less than t of xj less than L squared, this probability is going to be bigger than e to the minus constant t over L squared. Because we do rounds of length L squared. In each round, we have a constant probability, and we have t over L squared round. After we do that, we know that we stayed in the interval. I'm sorry, maximum here. Sorry, I want the maximum to be less than L, not L squared. Sorry. So here it's an L. So after we do that, we know that no lamps could have been turned on outside that interval. So all lamps that are on are in that interval. So if I want to get back to the identity, what do I need to do? I need to turn off all the lamps that I turned on. So now we want to lower bound the probability starting from the identity that xt is again is equal to the identity. And take t to be even, then this probability is going to be at least, well, I can lower bound it by the probability of staying here, e to the minus constant t over L squared. And then I need to turn off the lamps that were turned on. What's the chance of doing that? Well, there are only 2L lamps. So I just need, so I'm going to dictate, so I'm going to leave, instead of running all the way to time t, I'll run to time t minus 2L or 4L. And then I'm going to do in the last moves, I'm going to just turn off all the remaining lamps. That's just going to cost me something exponential in L. So you can get a lower bound of this form. And when you see this, you see why we want to choose L, which is t to the 1/3, to optimize this lower bound. Because then it equalizes both these terms and gives us e to the minus another constant, t to the 1/3, as a lower bound. So this Veropoulos bound is optimal. And so this kind of calculation was first done by Alexopoulos shortly after Veropoulos' theorem in the 80s. So e to the minus t to the 1/3 is the best you can do. So heat kernel, so if you want to prove things by heat kernels, you won't, you can't get anything better unless, see here, unless you prove better off-diagonal bound. So here we used an on-diag. So this is a uniform bound. It doesn't depend on what x and y are. But you expect that if y is far enough from x, should be able to prove a better bound. And there are some improvements like that, but they're not good enough. And there's no heat kernel proof that gives something better than this t to the 2/3 in general. In specific examples, heat kernels can give you a lot of information, but in general. So it's a problem I've been interested in for a very long time in the infinite case. And so I was kind of shocked back in 2005 when I learned from an email by Anna Erschler that there is a proof that she knew how to prove T. She knew how to prove something like this for infinite groups. And her argument, again, she never wrote it down, but the argument goes like that. Well, if the group is, so again, I'm going to refer to some non-elementary things. Later we'll give elementary proofs, but so if the group is non-amenable, the walk has a positive speed, so everything is true. If the group is amenable, then there is a theorem of Mach, which says that there is a equivariant harmonic mapping from the group into Hilbert space, and applying that gives you a Hilbert space valued martingale, and for the martingale you can get a lower bound on the growth just using orthogonality of the increments. And then because this mapping is Lipschitz, you get a lower bound on the growth of the walk in the group. And this theorem of Mach, the original paper of Mach, is extremely hard to read even for experts. You can look at the math review of it by Alain Valette, who complains. But later, this theorem of Mach has a simpler proof. So there's a fantastic paper of Kleiner on Gromov's theorem, where in the appendix he gives a reasonably short proof of this Mach theorem using ultrafilters. So it's still kind of mysterious, but it's readable. So anyway, with James Lee, we wondered, can we give a direct elementary proof? And we did. So there is a paper in Annals of Probability which proves bounds in a direct way. And actually, after we did that, we could also reproduce this Mach theorem of building a harmonic mapping into Hilbert space, but I won't go into that. So now what is our, this is a paper with James Lee that appeared a couple of years ago in Annals of Probability, I think 2013. And it's about kind of general transitive chains. So more general than Cayley graph, but let me just focus on the following two special cases of the theorem in that paper. So it says if G is an infinite Cayley graph, then the expected distance squared from x0 to xt is at least t over d. So d here is the degree of the Cayley graph, so just the size of the generator set. So no mysterious constants, just t over the degree. And OK, so in general, I need a condition like t large here, t large enough. But if G is amenable, this is true for all t. And then for G finite, we're going to get essentially the same thing. So expected distance squared from x0 to xt. I'm going to lose some constants. So let me put t over 2d. Just lose a 2. And here t has to be small. So t less than, well, 1 over 1 minus lambda 2, which we call the relaxation time. So for G finite, the random walk is just a finite Markov chain. And it has a top eigenvalue of 1, second eigenvalue of lambda 2. This is connected because S is a generating set. So lambda 2 is strictly less than 1. The gap, 1 minus lambda 2, is called the spectral gap. It's also the first eigenvalue of the Laplacian on the normalized Laplacian on the group. And 1 over that is known as the relaxation time. It's a close cousin of the mixing time. It's generally smaller. And the ratio is bounded by the log of the size of the group. So for all times which are less than the relaxation time, we have the same kind of lower bound. Let me already tell you an open problem. Can you replace the relaxation time here by the mixing time? This would have dramatic consequences. And I'm willing to replace the 2 here by 1,000,000. But we don't know that. So the best general bound we have of this type is until the relaxation. Okay, so I'll show you a really elementary proof of this, but it is motivated by this non-elementary mock embedding, which you don't need to understand, but this is what, otherwise the steps look maybe a little magical or mysterious, but they came naturally. Okay, so the proof of both the finite and the infinite case are unified. I'm going to give all details for the finite case. The infinite case needs the spectral theorem for self-adjoint operators in a Hilbert space, but still, even the infinite case is self-contained at the level of a first-year graduate course in analysis. But for the finite case, which is, after all, the focus of this workshop, I'll give all the details. And so there is a unified proof, and it's based on the following lemma. So take any function f which is in the space L2 of G. This is just, right? So we have G is finite or infinite. L2 of G is just functions from G to the reals that are square summable. If G is finite, it's just all functions from G to the reals. And for any function like that, what they claim is that the expected distance squared between x0 and xt is going to be at least 1 over d times the Dirichlet form Et of f over E1 of f. So let's take f, which is not a constant function. And what is this Et? So Et of f is a Dirichlet form. So I'll write it explicitly in the two standard ways. So one is you sum over all xy in G, f of x minus f of y squared times ptxy. So often one has a pi in the background, but here we're working with just counting measure as the background measure. So it's just this, and I'll divide by it 2. And because the simple random walk is reversible, there is an alternative representation which is useful. So if you take this square and expand it, so you write it as fx squared plus fy squared minus 2fx fy, and you look at each term separately, well, what contribution does it give? So if you just take fx squared multiplied by ptxy and sum over xy, well, the sum over y of ptxy will just give you 1, so you just get the sum of fx squared. The same story happens with fy squared, because ptxy, p is a symmetric matrix here, so it doesn't matter. And the interesting term is the diagonal term, so this 2 cancels with the half, and you have sum fx fy times ptxy. So overall, we see what you get is just can be written as an inner product, I minus pf times f. This is just I minus p to the t, thank you. Okay, so the I gives you f times f, which is just half of the contribution of these 2 terms. And p to the t f times f is what you get from the diagonal term, just by definition. Okay, p to the t, just the tth power of the matrix p. P to the t f, inner product with f, definition of the standard scalar product, and you get this identity. So these are the 2 standard representations of the Dirichlet form. Okay, and in particular, if f is not constant, this is not 0. And so the lemma says any function f you plug in gives you a lower bound on the expected distance squared, and then you have to choose the function. So before proving this lemma to you, I want to show how it's useful. So let's call this finite case star. And before proving the lemma, let's see it's useful. So let's prove star using the lemma. Okay, so now we're in the finite case. We want to prove a lower bound on rate of escape, but until some time, which is the relaxation time. So we have to choose f. So now G is finite. What f's can we choose? So the fact that the eigenvalue is entered in the statement should give you a hint what f to use. Eigenfunction. So let's take an eigenfunction. Pf is lambda f. And we could use any eigenfunction, but we'll get the best bound with if we take lambda equals lambda 2. And we can normalize the eigenfunction to have L2 norm 1. And then we can just calculate what is so we have that bound. What is Et of f? It's 1 minus lambda to the t over 1 minus lambda. Right? So it's very easy to take p to the t, apply it to f when f is an eigenfunction. And again, right, so ff was 1, or in any case it normalizes in the top and the bottom. So we just get this explicit expression. Now because we assume that, so we go here, t is less than 1 over 1 minus lambda. So this means that lambda is bigger than 1 minus 1 over t. Right? That's just rewriting this assumption. So this is bigger than 1 minus 1 over t. So, okay, you have to. So this expression, of course, it's also the sum of lambda to the j from 0, 0 to t minus 1. So this expression is monotone in lambda. So we can use this bound and plug in the 1 minus 1 over t because of the monotonicity that we see from this expression. And then so we get 1 minus 1 over t to the t divided by 1 over t. So and I still have the 1 over d on the outside. So this term gives me the t over d. And then this term is at least 1 minus 1 over e. Okay, so even bigger than a half. Okay? So now we have some motivation to prove the lemma. So it's going to be based on spectral embedding. So we're interested in distances in the group. This is a metric space we don't know well. The metric space we understand best is Euclidean space. So let's get everything mapped into Euclidean space, or in general a Hilbert space, and try to work there. So how we're going to embed, we're going to take a function f, capital F, from G to the Hilbert space L2 of G. Again, for the finite case, this is just Euclidean space. And so what is the embedding capital F? I said it's a spectral embedding. And in general, a spectral embedding is obtained by applying different eigenfunctions to every element. Here we're just going to choose not all eigenfunctions, just those that are obtained by spinning around this top eigenfunction, little f. In other words, f of x, so x is an element of G, f of x will be the vector little f of gx as G runs over G. Okay, so for every element x, I take little f of gx, and as I run over G, I get a vector in the space L2 of G. Okay, so this is capital F, and let's see how does this capital, so the idea is that we want to understand distances for the walk. We'll map into this Hilbert space and see distances there and then kind of convert back. So for this, we're going to start x0 at some initial point, little x0, fixed point in the group. And then we're going to compute the expectation, starting at that point, f of xt minus f of x0, norm squared. Okay, and this is the Hilbert space norm in L2G. Okay, so this norm squared, well, let's write it explicitly. We know what capital F is. So this is the expectation, starting from x0 of the sum over G, f of gx, 0, I'm sorry, f of g xt minus f of g x0 squared. Okay, I just wrote what is capital F and the definition of the L2 norm. But now, as G, suppose I write this as little x. So x0 is a fixed point, say the identity of the group, but it could be any fixed point. So as G runs over the group, gx0 also runs over the group. So call this x. This will be another index running over the group. And now if I do, now the random walk I'm doing here, maybe I should have emphasized, is a right random walk on the Cayley graph. So each time we choose an element of the generating set and multiply from the right by that element. So if I do a right random walk starting at this point x, gx0, after t steps, I'm going to have the distribution just of gxt, because multiplying from the left and multiplying from the right are operations that commute. So in other words, I can write this in the following form. It's the sum, double sum over x, y, and g. Here I have f of y minus f of x squared ptxy. So it's just a matter of reindexing. So this we call x, this we call y. Observe that this y is obtained from x by running t steps of the random walk. And this x is just running over the whole group, and you get this expression. This is just twice the Dirichlet form at time t of the function little f. Right? Now, we're going to apply this twice. First time, let's apply this for t equals 1. So suppose x0 and w are two neighbors in the Cayley graph. And let's look at 1 over d times the distance squared, the norm squared of f of x0 minus f of w. Well, this is less than the expectation, starting from x0, of norm fx1 minus fx0 squared, because when I calculate this, one of the choices of x1 is this w, and it is taken with probability 1 over d, because I'm doing simple random walk. So this expression is just a sum, and this is one of the terms in the sum. So I have a sum of positive terms. So this inequality holds. And this is just what we just calculated for t equals 1. So this is twice E1 of f. Now, why did we do this? Because this tells me that, so norm of fx0, let's minus fw, is less than So we move the d, we get root 2d E1 of f. So for any two neighbors, x0 is arbitrary, w is an arbitrary neighbor. For any two neighbors, the norm of the difference after apply f is bounded by this number. So in fact, f is Lipschitz. So f is a Lipschitz function with the Lipschitz constant of f is at most this number. Root 2d E1 of f. So by Lipschitz constant, I mean, as usual, that if I take any 2 points now, not just neighbors, f of, and I apply f, the distance can grow by at most this factor L. And that's just true because in G, in the Cayley graph, the distance is given by the shortest path. So just adding this over the shortest path, I get this inequality. Okay? So again, this means for any 2 points, x and z, not necessarily neighbors, fx minus fz, the norm is bounded by this Lipschitz constant times the distance in the group from x to z, just obtained by summing. So now we're going to use that. So let's take this calculation. So I write it again, Et of f, twice Et of f is equal to the expectation of norm fxt minus fx0 squared. So I just rewrote what we proved before. But now we want to use this fact on the Lipschitz constant. So this is bounded by this. So this norm, this is at most L squared times the distance between x0 and xt squared. Right? That's the definition of the Lipschitz constant. Okay, so and this, so and remembering that L is at most that, we get 2d E1 of f times expected distance from x0 to xt squared. And we're done. Right? Just move this downstairs, and we have the claim of the lemma. Okay, so it's all very simple, no difficult steps, but it came from somewhere. Any questions?
Not from years of fooling around.
What?
One keeps tinkering with it.
Yes. And eventually, yeah. So.
Partially that, certainly.
Right. You can't.
Nice sort.
So. So how can you go further? So what about the infinite case? So I won't go into details in the infinite case, but one thing that works there is, so the problem is the infinite case we no longer necessarily have eigenfunctions, but the spectral theorem gives us approximate eigenfunctions, which can be with suitable epsilon and deltas can be used in this proof. There is a more instructive argument where you can take this function f to be the occupation time of a Fellner set. So in that theorem for the infinite case, you have to separate the case when the group is non-amenable and you move in positive speed, and the group is amenable. And in the amenable case, you have large sets with small boundary, and you can define a function which is how long do I spend in this set? So that's a function of the starting point. And it turns out that you can calculate things for that function, and you get the sharp bound this way. This is all detailed in the paper, and actually there's an exposition of most of what I'm talking about. I've recently added to my book with Russ Lyons, and you can find it in that book. An exposition, or you can look in the original paper for more general things. Now, let me mention one thing that follows from this star. So if I take so this is true for all t at most T-rel, but if I specialize to T-rel itself, I'm going to get an inequality that was already known. So, so take T, which is T-rel. So T-rel over 2D is bounded by this. And what can I say about this? This is certainly at most the diameter squared. So I'll write capital D squared. So capital D is the diameter of the Cayley graph, the largest distance. So certainly rho is at most the larger distance. So okay, so the relaxation time, this inverse spectral gap, is at most the diameter squared times the degree. Well, here I got an extra 2 or some constant. With more care, one can actually prove this clean bound without the 2. And this is already known by different proofs. I think the first one is due to Babai in 91. And so he didn't prove this general estimate, but this kind of estimate. And there are other proofs using the method of canonical flows initiated by Jerome and Sinclair and refined by Diaconis Strouk and others. So this has, we know kind of 3 different proofs of this. So we're pretty confident it's true. But
and we were, as you know, trying to bound the spectral gap, which this gives if you switch terms.
That's right. Yeah. So this gives you a lower bound for the spectral gap, right? That's the same thing. But here is an open question. Is it true? So now I'm going to, so for going from relaxation to mixing, there's always this annoying issue of periodicity. So when talking about T-mix, I'm going to switch to the lazy simple random walk. Again, on a Cayley graph G. So G is still a Cayley graph. And then I ask, is it true that T-mix is at most D squared times, well, times D times a constant? So this seems to hold in all examples we know, and I've been scouring all the examples I know and asking people who know more groups, and haven't found any counterexample to this, but no proof either. What we do get from this, so there's a classical relation that, of course, the mixing time is at most the relaxation time multiplied by, in this case, log of the size of the group. So T-mix, which is less than T-rel times log G, okay, with a constant here. So it's big. So this is a general easy upper bound. So we get big O of D squared times D times log G. So in other words, if I'm thinking of the degree as a constant, then I get a bound of the diameter cubed, right? Because at least if the degree is bounded, then the diameter is at least log G. Anyway, this is under a further assumption, but this is without any assumption. So we have diameter squared times degree times a log factor is true, but there's no example known where the log factor is needed. So now this is connected to the question I asked before. So we look at this inequality for infinite groups. This holds forever. For finite groups, it has to stop. But when does it have to stop? So we know it stops at the, it's true until the relaxation time. I believe it certainly holds till the mixing time. And maybe it also holds until a time which is essentially the diameter squared over the degree. So the question I find kind of intriguing, you're walking on a Cayley graph, doing a random walk. you see maybe just your local neighborhood. That's all you need in order to run the walk. But you record somehow the distance to the starting point. When do you start to feel the walls closing in around you and the fact that you are in a finite group? There isn't this infinite space out there. You're stuck in a finite group. How long? Eventually, you have to feel it, your distance, recording the distance. It has to get stuck. But when do you have to feel it? My guess is that you only start slowing down when your distance is of the order of the diameter of the group. As long as your distance is little o of the diameter, you shouldn't feel that you're in a finite Cayley graph. But we have no proof of anything like that.
Most useful about for simple groups?
Sorry?
For
So,
finite simple groups?
so I don't know any general bound like that. So, but you know, I haven't attempted to look at special classes, you know, various, but to prove it in special classes. I'm mostly trying either to get a general proof or find a specific group that is a counterexample. But certainly, people who know more group theory, you know, may want to look at this and prove it for classes of groups, or maybe find a counterexample. Okay, so I'm going to finish in a minute. You know, I was so I mentioned heat kernel bounds, which can't prove this, and I gave a talk in Harvard a few years ago. Yao was there, and I mentioned that heat kernel bounds are not good enough to prove this, and somehow this made him very angry. So he really likes heat kernel bounds, and I like them too. But just they're good. I mean, they are good for their own purpose. But for this purpose, right now they can't compete yet with the embedding, Hilbert space embeddings. So I want to mention two more things, or a few more things. One is, so here we got a lower bound for the distance squared. We'd like to refine it to say that actually the distance, they say the expected distance is bigger than root t. This is true, constant root t. This is true, but it's not obvious because it's going, you know, against the direction of Cauchy-Schwarz. So one way to do that is to actually produce a martingale where you have Burkholder, Davis, Gandhi bounds that allow you to pass between different powers. And so where is the martingale? So I told you this abstract Mach theorem that says there's harmonic mapping. And we can get it from this proof with some careful passage to the limit, which I won't go into. But let me show you in the finite case where is. So you have a simple martingale. So the proof, there is an alternative version of the proof I showed you, which gives more, which is to use. So if you take the, you know, the distance from. So instead of the distance from x0 to xt, if you use f of xt, so okay, which version do I want to use? Maybe I'll just use this. So if you use f of xt, where f is this eigenfunction we were talking about before, then this is not a martingale. But the expected value goes down by a factor lambda in every step. So if we take this and, you know, divide by, do lambda to the minus t, this is a martingale. This is a real valued martingale, so it's not good enough. But if you work with lambda to the minus t capital F of xt, where f is that embedding we used here, then we get a Hilbert space valued martingale, which works fine for the finite case. And then one can just adapt the proof I gave you, working with this martingale, and then using martingale inequalities to get, you know, sharper versions of this estimate. So in particular, you can get that the expected distance from x0 to xt is at least root t, and other powers as well. So
what goes wrong with the first martingale?
What goes wrong? So well, what goes wrong is that you don't have control. So in order to show that you need a lower bound on the conditional variance in every step to show that the martingale is. So So the idea is to show that this martingale is actually growing. So you want to show that its variance is growing linearly. So the variance is a sum of, well, expectation of a sum of conditional variances along the way. If you just look at this one little function f, you have no control. Maybe it has some flat areas, and it does have some areas where it's not changing much. And if the random walk wanders into those areas, your martingale is not growing. However, by doing this spinning, you get something which everywhere it grows by something, and it's just rewriting the proof I indicated, I showed you, shows that the Hilbert space-valued martingale here, this capital F of xt, no matter where you are, it's just averaged enough. So no matter where you are, your conditional variance actually doesn't depend on where you are. There's enough averaging. And so it's always bounded below by essentially constant over the degree. And so you get this linear growth. Okay. So I'll talk more about, so heat kernel bounds are interesting in their own right. They're related to the geometry of the Cayley graph, the isoperimetric profile, and I'll explain that next time.